So happy Wednesday, welcome back. Looking at the calendar, we see we're very near the end. Just handed out take-home quiz number, I think this is our fourth one. This is the last quiz of the semester. Same rules apply. You can make an index card with anything you want on it, but you have to make the index card before you start the quiz. And there's an estimated time limit or recommended time limit, something like that. This one is going to be shorter than any of the other ones before. I think this one is a 14-minute recommended, and you can take up to double that amount of time. So it shouldn't be as long as the others. Today is our last day of new material. On Friday and Monday as well, we have review days built in for the final exam, so nothing new after today. And then the exam itself is 1 week from today, right here in this classroom at 10:30. Questions on the calendar? Okay, and also the last project is due at the date of the final exam, but if you have it done early, throw it in the folders, and it'll be one less thing to worry about during the last hectic week. Okay, so one other announcement. So I know that many of you have already registered for the spring semester, but if you haven't, I would encourage you to do that soon. In the last week or so before a semester starts, there is a mad rush where lots of people come in and try to register and discover that most of the classes they want are full. And so I will say that this would be a great opportunity to avoid that rush. So meet with your academic advisor over the next week, or if you don't know who that is, ask me after class and I'll tell you. Your academic advisor is probably not going to be here much in January, but the advising center is, and so they can get you registered even if you can't locate your official advisor, right? So I'd encourage you to register so you avoid that rush. All right, so at the top of page 69, our daily summary. Kyle? Okay, number 2, Brendan. Okay, so suppose that you're faced with this integral right here, integral from a to a, f of x dx, same number at the top and the bottom. So you can think about you can think about integrals as being an area, right, between these two vertical lines and under a curve. What happens if these vertical lines are exactly in the same spot? Then you have 0 area. So it doesn't matter what the function is, we define this kind of integral to be 0. And now the next one is the integral from b up to a. Like if the numbers are in reverse order, normally the bottom number is the smaller one and the top number is the bigger one. So if they're reversed, you can think about, so like if we think about a velocity curve, what does the area tell you about the object? It's the distance traveled, right? So as you sweep out area to the right, you got this distance traveled. So what if you imagine starting at the end of the trip and your distance traveled kind of watching this person go backwards? So you might say instead of walking 5 feet, they walked -5 feet. And so here's our definition for this guy, is that if the numbers are in like the wrong order, you put them in the right order, but then pay for it with a negative sign in front. Okay. So anytime you want to swap the order of those limits of integration, go ahead and do it and put a negative in the front. Okay, so let's try these examples here in number 3. We're trying to evaluate these integrals without the calculator. Calculator will make quick work of them, but there are some integrals we can do by hand. So this first one, integral from 3 to 3. I don't need to read anything further. It doesn't matter what's inside. What's this equal to? 0. Right? Same number on top and bottom, automatically 0. Easiest question on the test. Part B, integral from 1 to 0. What looks strange about that? It's kind of backwards, right? Like the smaller number is usually on the bottom. So how about we put the smaller number on the bottom? 0 to 1, copy the whole thing just like it is. And then how do I make it so it's really equal? Negative. Okay, so let's think about this integral, and we'll deal with the negative sign. We'll just stick it in at the end. So the function y equals 1 root 1 minus x squared is this. It's actually just part of a circle. And so we're integrating that circle between 0 and 1. So there's your 0 line and there's your 1 line. 1 line. And so I'm interested in the area of that quarter of the circle. So what's the area of the whole circle? Should be pi r squared. Radius is just 1. So the area of the whole circle should be pi. The area that we want is a quarter of that, right? So then the answer to this problem is just a quarter pi, but negative. That's the answer. Okay, so when the numbers are in the right order, then the definite integral just means area. But in this case, we had them in the wrong order, so it meant the negative of the area. Okay, so here's some equations we're going to fill in, some properties of definite integrals that just have to do with area. So the first one says, suppose you got this integral of the sum of two functions. Two functions have been added together. So it turns out we can think about separating these into two separate functions and finding their individual areas and then adding them at the end. So this equation becomes integral from a to b of f of x, and then don't forget the dx is required to be there with the integral sign, plus a whole separate integral, a to b g of x dx. If you want to find the derivative, not integral here, but derivative of like 2x minus 5x squared, that's easy, right? You just separate it and you don't even think about the fact that you're separating them, right? And it works out nicely because subtraction is totally fine for derivatives, and addition is totally fine for derivatives. What gets harder is multiplication and division, right? You have a separate product rule and quotient rule. But just like addition is nice for derivatives, addition is also nice for integrals, and so is subtraction. So this guy is just integral from a to b f of x dx, and then minus a brand new integral. Okay, the rule in part C has a constant multiple c times the function. Let's just go back to derivative stuff. Way back when you were asked to find the derivative of 3x squared, I mean, instantly right now you know it's 6x. But before we knew that, we had to take that 3, and did it disappear or did it stay? It stayed, right? And then you would just multiply the 3 sitting there by the derivative of x squared. So it's the same idea with the constant multiple of a definite integral. The constant can just stay there waiting for you to find that area, and then it's going to multiply in at the end. It's like the same nice rules for derivatives work for integrals. Notice that we don't have a rule up here that says the integral of f of x times g of x. Just like derivative of that is complicated, product rule, it's complicated here too. We don't have an f of x over g of x. Quotient rule is complicated, it's complicated here. Okay, but there's this one thing that says, okay, suppose you're going from a to c of this function f, and then the same function f, you're going from c to b. Can you guys imagine, let's look at this picture in number 5, and then we'll fill in the blanks for that rule. So the first integral from a to c represents this area right here, right? And then the second integral from c to b represents that area. So we could have just done this as one integral from a to b, right? We didn't have to stop in the middle. So this is really just the integral from a to b. If they overlap, if what overlaps?
Like if it's, let's just throw in like a
yeah.
And then it's like A to the
Mm-hmm.
and then C to B.
Okay, so if you're going from like A to D and then C to B, then there's an overlap and there's a problem. So that's not this formula. Turns out this formula works even if C is on the wrong side. Like I'll draw kind of my funny thing there, and there's my A and there's my B. And suppose that C is like out here and we get this part of the function that isn't even pictured. Turns out you can still go from A to C and then C to B And it's the same as this a to b. Do you see why? Because, yeah, you go from A to C and you get this extra stuff, right, between B and C, which I wasn't paying attention to. But then when you go C to B, you just subtract off that exact same extra stuff. So it makes no difference whether C is between or way out in the ether. Okay, so let's try number 6. Again, we'll do this one by hand and then we can check on the calculator. So I have an integral. Fundamentally, I see two functions up there with what sign in between them? Inside of here, I see two functions. What operator is between them? Subtraction, right? And is subtraction nice or not nice for these integrals? It's nice. So that means we can write this as the integral from 0 to 1 of, what's the first function? 5. Then don't forget the dx. And then minus brand new integral, still from 0 to 1. Three times root 1 minus x squared dx. Okay, so far so good. I'm going to copy that first guy because there's something further we can do with the second guy. Yeah, that 3 is a constant multiple. And constant multiples can come right outside. And just wait until the end. So it becomes 3 times the integral of just that square root. Yeah, so now I think it's just a matter of filling in because it should be easy. Integral of 5 dx. Y equals 5. What does the graph look like? Just a horizontal line. So when we sweep from 0 to 1, just a rectangle. So 5 times 1, just 5. Minus 3 times this integral we saw. What is that integral equal to? Pi over 4. So there's our answer. 5 minus 3 pi over 4. Okay, so the activities start on the next page. You're going to really try to explore, really try to think about these properties, write more stuff out than perhaps you feel you need to, just to make sure you're clear on what the properties are saying.